And good morning. It is Tuesday, August 22nd, year 2023. My name is Mark Kulak, 9:49 a.m. in the morning, Eastern Standard Time. And what we are going to be doing today is continuing playing the audio book from Audible on Gene Machine. Gene Machine is the book from, or I should say written by Venki Ramakrishnan, Nobel Prize winner. The Race to Decipher the Secrets of the Ribosome. I actually have the title as a secret, the Race to Decipher the Ribosome. But whatever. I think you get the general idea here. Oh, boy. I wish I didn't have to do this part here. Anyways, we played up to Chapter 9 last time. And today we are just going to be continuing on with Chapter 9. Chapter 9 is getting started in Utah. And I'm just going to click play here. You'll notice the chair is going to be emptying out. I have still, as I've said before, the stuff to do. And what's great about playing the audiobooks is you get to listen to and absorb some of the information. So far, very good book. I'm going to need to listen to it at least a couple of times to understand, especially all the stuff related to crystallography. And this chapter starts off with Venki's time at Utah. And it's a time at Utah I'm really interested in. I'm looking forward to him talking about the work he did with a fellow named Dr. Wes Sundquist. So with that said, without any further ado, we're just going to start this chapter, and we will play until it gets hung up. Last time, one of the chapters actually just stopped playing, strangely enough. And I have no idea why, but we reposted it, took out that dead spot, and hopefully we don't have that problem again, and it just plays until we can't play it anymore. All right, that's all, everyone. Thank you.
Chapter 9. Getting Started in Utah. Starting all over again in Utah was depressing at first. In Brookhaven, I had left behind a well-equipped working lab with a couple of excellent associates who understood the work, and lots of colleagues who knew and liked me, had helped me grow into an independent scientist, and had taught me crystallography and the tools of molecular biology. For quite a while, I was alone in the lab. I was used to working on my own, and for several months, students and postdocs would pass by the hall and see the curious sight of a lonely full professor unpacking boxes and setting up equipment and trying to get some work done. However, people in Utah were very welcoming and supportive, and within a year I had assembled a group working on the ribosome that consisted of 2 graduate students, a postdoc, and a technician. In addition, there were others who worked on chromatin, including Bob Dutnell. It was a motley crew. Our bread and butter project was still the work from my grant from the National Institutes of Health, NIH, with Steve White, to bang out structures of individual proteins in the ribosome. Since there were a lot of proteins, it might have kept us going for a while. But by then, I was totally convinced it had become a protracted stamp-collecting exercise, and my heart wasn't in it, even though I tried to talk it up. But it was a good way to train new people in crystallography by starting them on a project that wasn't too difficult. The first to join was Bill Clemens, a big, tall African-American with short hair and large glasses, who insisted on spelling his first name with just one L to distinguish himself from his father. He came from a highly accomplished family. His father was a U.S. Marine Corps captain, where he was the conductor of their band, and his uncle Clarence was the saxophonist in Bruce Springsteen's E Street Band, a role now taken up after Clarence's death by Bill's brother, Jake. Bill arrived with a combination of enthusiasm and naivete and a touch of immaturity. At some point after he joined my lab, he stopped cutting his hair, braiding it into dreadlocks as it grew longer and acquiring a distinctly Rastafarian look. He was extremely social, with a fondness for barbecues, beer, and hip-hop music. As a vegetarian and near teetotaler who liked mainly classical music, I was about as far from him culturally as one could get. But somehow, we hit it off. Bill initially tried out my lab by doing one of the first-year rotation projects for graduate students. During his short stint, he had managed to get crystals of S15, a small ribosomal protein. At the end of the year, he had to decide where he wanted to spend his next few years for a PhD. At the time, my nearly empty lab might not have seemed very attractive compared to the thriving labs of Wes Sundquist and Chris Hill next door. But with S15, he already had a working project, and that helped to sway him. We had a chat, and I told him that he could start working on this protein, but really, I had my sights on the whole 30S subunit. I thought he'd be skeptical, especially on learning that Ada's large, well-funded group in Germany had been unable to crack its structure even after many years. To my pleasant surprise, his eyes lit up. I thought it was best for him to tackle a couple of smaller proteins first, so he could learn the basics of solving structures before going on to the 30S. Bill's energy and optimism, and his willingness to try new non-standard approaches were all invaluable in the years to follow. The next to join was Brian Wimberly. He had called me about joining my lab in Brookhaven, but I told him I was moving to Utah, so he waited and contacted me a year later. He had obtained his PhD from Berkeley under Ignacio Nacho Tinoco, where he was using a rather different method called NMR, nuclear magnetic resonance, to show that a piece of RNA in the ribosome had an unusual structure. He had worked on calcium-binding proteins during his postdoctoral work at the Scripps Research Institute in La Jolla, but never quite got over his romance with RNA. Towards the end of his postdoc, he had to decide whether to take the unusual, possibly foolhardy step of turning down a faculty job at Georgia Tech or do a second postdoctoral stint with me to learn crystallography. I was eager to recruit Brian, who had real expertise in RNA structure, something I knew little about, even though the ribosome was 2/3 RNA. Brian came to visit me, and we hit it off right away. I had told him what a great and safe place Salt Lake City was, but when we emerged from my house the next morning, someone had smashed the windows of every car down the block. I was worried that this would derail my efforts to recruit him, but luckily, Vera took him for a hike up the foothills surrounding Salt Lake City, where they saw lots of wildlife on a beautiful spring morning. Since he loved hiking in the outdoors, that sealed the deal for him. The very next year, John McCutcheon, a smart, cocky, and ambitious student from Wisconsin, wanted to join the lab. I thought he could start off by working with Brian to get crystals of a ribosomal protein that bound to a small defined piece of RNA, but he soon felt this was too pedestrian and quickly decided to go for broke by working on the 30S structure. So now I had two students committed to working on 30S. Clearly, the fact that neither Bill nor John knew much about either crystallography or the ribosome had made it easier to convince them that this was a good thesis project. The problem was how to begin. The crystals of the 30S subunit, first reported by Garber's group in Russia, were from Thermus thermophilus. However, almost a decade had passed since those crystals were reported, and they still did not diffract well enough to give an atomic structure. In considering how to improve those crystals, I remembered Joachim Frank's talk in Victoria. He had not only shown images of the whole ribosome with tRNA, but had also shown that the 30S subunit had slightly different shapes depending on whether it was by itself or part of the whole ribosome, suggesting it was a rather flexible molecule. The subunit was described in anthropomorphic terms as having a head that is connected to the rest of the body by a slender neck, and the head was tilted slightly differently in the different structures. It was as if the head could wobble. Large molecules often have to be flexible to work. The movement of the head turns out to be crucial to allow tRNAs to move through the ribosome. But flexibility is terrible for getting good crystals, which depends on all the molecules being exactly the same and sitting in the same way in the crystal lattice. Perhaps, I thought, this floppiness of the head was why the crystals of the 30S subunit weren't good enough. If so, the solution would be to somehow fix the head so it couldn't move about. There is a protein that helps the ribosome get started at the right position on the mRNA called initiation factor 3, or IF3, and it was thought to bind right between the head and the body of the molecule. We had just solved its structure during my last year at Brookhaven, so it was on my mind. I suggested to John McCutcheon that he try to lock the 30S subunit by binding IF3 to it, and then try to crystallize that. With Bob Dutnell's help, we used a chromatographic column to purify away the 30S subunits from any contaminants, especially enzymes called ribonucleases or proteases that could destroy the ribosome by degrading its RNA or protein. This was important for two reasons. It meant the 30S subunits could sit in drops, waiting to crystallize for weeks and remain intact, but it also had the effect of removing one ribosomal protein, S1, that is more loosely bound than the others. The result was we had a very pure sample of 30S subunits. Before binding IF3 to the 30S subunits, we decided to check if these 30S subunits were good enough to crystallize at all using what was already known. Even though the best reported crystals to date were not good enough to yield an atomic structure, even a low-resolution structure could still tell us a lot about how the RNA was folded. We'd also be able to place proteins whose structures had already been solved in isolation and slowly build up a piecemeal model of the subunit. That could keep us busy until we got better crystals. Within a couple of months, we had reproduced the original Russian crystals. They were pretty small, and some initial tests showed they diffracted to quite low resolution, worse than the best ones reported so far. However, they were slowly getting bigger. Just as we had embarked on the 30S project, Steve White and I were invited to a meeting in Sweden on the structural aspects of protein synthesis, that is, the structures of anything to do with ribosomes. The organizer, Anders Lilas, was collaborating with Maria Garber on individual ribosomal protein structures, and they were friendly competitors of our effort with Steve. Even though I was already bored with the work, it was an opportunity to go and see what was happening. Not only would Ada be there, but also Peter, so I would see what the competition was up to. There was also another reason to go. I could visit the LMB in England again, since it was practically on the way to Sweden. This was not merely for a nostalgic social visit. Rather, I had come to the conclusion that it was the best place for a risky project like the 30S structure and wanted to see if I could work there. Ever since embarking on the 30S project in Utah, I was excited, but also quite fearful. What if it took me years to get good crystals? Even if I got them, what if my ideas of how to solve the structure didn't work out? The problem with doing it in a university setting like Utah was that my research depended on grants, which last only a few years before you have to renew them. These grants are typically funded by the National Institutes of Health, after being reviewed by a panel of a dozen or more experts in your field. In theory, that is a great way to fund science, and it has worked extremely well. But one scientist described the system as being like your favorite restaurant. You don't want to go into the kitchen to see how the food is being made. There are two problems with these expert panels. On the whole, they tend to be too conservative and lack the vision or confidence of judgment to support bold, original proposals, preferring incremental ones where the work is clearly feasible. The only way to ensure you fill the panels with the really top scientists who are unafraid to back adventurous ideas is to make it like jury service. So if you receive an NIH grant, you are required to serve if called. The other problem is that each panel receives over 100 proposals, each with more than 50 pages of dense information. In practice, each application is read in detail by only a couple of people, called the primary and secondary reviewers. Because only a small fraction get funded, even if one of these reviewers isn't enthusiastic about a proposal, it is essentially doomed. Once, when I had argued against the primary and secondary reviewers to try to rescue a proposal, everybody else just split the difference and gave it an average score, so it was doomed anyway. So although the process is fair on paper, in practice it can be somewhat arbitrary, particularly when it comes to risky or highly original proposals. Having served on these panels, I could just imagine how they would receive a proposal from me on the ribosome. I didn't have crystals, but thought I had an idea of how to get good ones. And although a well-funded group in Germany had been unable to solve a structure with good crystals for years, I just had an idea of how to go about it. I could just hear the peals of laughter that would go around the committee room as they dumped my proposal into the bin. The other option was to divert resources from my existing grants to do the work on the side, which many scientists have done to do their most creative work. But given the competition and the need to focus on it completely, I didn't think this was a viable strategy. Also, if the ideas didn't work, I would lose my grants and would have to start from scratch, and I might never recover. Every research university has people who lost their research funding and ended up being second-class citizens, whom their department tries to force out or marginalize. But the LMB was somewhat different. They understood that some problems can take a long time and, more importantly, had a lot of people who knew what it took to crack them. So, even though I'd already approached them about a job when I had just returned from my sabbatical, I wrote again to Richard Henderson, who by this time had become the director of the LMB. This time I had a concrete proposition for them. I had ideas for how to crystallize the 30S subunit and solve its structure, and was interested in moving to the LMB to work on it. Could I stop off in Cambridge and discuss it with them on my way to Sweden? Richard said he'd be happy to see me. The visit to Cambridge was unlike any job interview I've ever had. For starters, there was no job. For another, they never once discussed any of the usual things like space, equipment, or, God forbid, salary. Rather, I gave a talk on the structures we'd solved of various ribosomal proteins. Then, all afternoon, I had a completely frank discussion about the ribosome problem with Richard and Tony Crowther, who, like Richard, was a renowned electron microscopist who had become a joint head or co-chair of the Structural Studies Division. We discussed who was doing what, why the field was stuck, how I might tackle it, what sort of difficulties I might encounter, and how long I thought it might take to get to an intermediate step where we could see recognizable features in the maps of the 30S subunit. This sort of free-flowing intellectual give and take was quite unusual for a job interview, even if there wasn't actually a job. Let's keep in touch, was their verdict. Despite the non-committal response, talking to them had made me feel it wasn't such a harebrained idea after all. So I went from there to Sweden, feeling pretty enthusiastic. Many meetings are held in remote resorts to force people to discuss science instead of going off shopping or seeing the sights. Tolberg, a quaint village on the banks of Lake Siljan in Dalarna province, many hours north of Stockholm, fitted the bill perfectly. Anders Löjes had started organizing meetings in Tolberg because he had grown up there himself and knew a charming resort hotel that was suitable for holding conferences of about 100 or so people. He was a big, jolly man with a cosmopolitan outlook, but he was still rooted in his traditional rural Swedish upbringing. After he retired, he went back to his ancestral home in Tolberg. He was known by just about everyone in the ribosome field, and his strength was that he liked to think the best of people and wanted them all to get along. Although this made him a popular and trusted figure, his diplomatic skills were to be sorely tested in the next decade. For the first time, I was going to hear Peter tell us what the Yale group had been doing with their crystals. What sort of data did they now have, and how had they gone about obtaining the phases that were essential to determining a structure? With normal proteins, a single heavy atom like mercury or gold can give enough of a signal to be seen directly in the Patterson maps we discussed earlier, which have peaks that correspond to the distances between the different heavy atoms in the repeating unit of the crystal. But as the molecule of interest becomes larger, the relative signal from the heavy atom becomes smaller compared to the rest of the protein until it becomes practically undetectable. So for larger molecules, people had tried using heavy atom clusters to get started. These clusters were small inorganic molecules that contained several atoms close together, typically tantalum or tungsten. At low resolution, the many atoms in the cluster would act like a single superheavy atom, so the signal from them could be quite large. Just such clusters had been used before, for example, to solve the nucleosome core particle or a large enzyme called Ribosome, which plays a key role in carbon fixation by plants. But the 50S was much larger than any of these. In looking into this problem, Ada had thought of using large tungsten clusters. These clusters had up to 30 atoms and might do the trick. Still, it was not clear that these large clusters would bind to the ribosome at all, or, even if they did, whether they would give a clear signal. In Ada's talks in Victoria or Seattle in the previous 2 years, there was no clear evidence that a heavy atom cluster had bound to the ribosomal subunits in her crystal. But then, in Peter's talk in Tolberg, there it was, a giant spherical blob in their Patterson maps. It was the first direct proof that they could see a heavy atom bound to the ribosome. They had gone on to confirm the result by an independent strategy. Apparently, Peter had been impressed enough in Victoria by Joachim Frank's electron microscopy maps of the ribosome that he thought they might be a useful starting point to analyze data from the crystals of the 50S. The method is called molecular replacement, and the principle is this. With X-ray data, as we discussed earlier, you measure the intensity of the spots, but don't know the phase, and you need both to reconstruct a three-dimensional image of the molecule. Normally, you would use the heavy atom method that Max Perutz and his colleagues had invented to obtain the phases. But if you can find a similar molecule whose structure is known, then you can figure out how this test molecule would pack in your crystal and calculate its diffraction pattern. You then use the phases from this test molecule with the actual measured intensities from the data to get an approximate starting structure for your molecule. Then, calculate phases from that starting structure to get better phases, and gradually bootstrap your way to a correct structure. People like Steve Harrison had previously used three-dimensional images from electron microscopy to get started on some of their virus structures, so Peter reasonably wondered whether it would work with Joachim's maps of the ribosome. At the meeting, Peter showed how they had been able to use one of Joachim's maps to figure out how the 50S subunit would sit in their crystals. The approximate phases from this exercise predicted the peak they had already seen in their Patterson maps. The resulting map of the 50S from their X-ray data was still quite low resolution, but looked plausible and recognizable. There was no longer any doubt that their strategy was working. Then Ada spoke. She started off by showing data on the 50S subunit, which showed that the cell dimensions, which is the distance between repeating molecules in the crystal, changed as you collected data. This meant that, because of radiation damage, the crystals were changing while you were collecting data on them. She said they were unusable, and the implication was that the Yale group was wasting its time. The irony of Ada rejecting the crystals her own group had developed, while the Yale group was happy to work with them, was not lost on me. I was a bystander in this rivalry over the 50S subunit, so up to this point, I was relaxed. That is, until Ada said she now had managed to get the 30S subunit to diffract well when bound to a heavy atom cluster. Presumably she had been looking for a heavy atom derivative, and one of them stabilized the 30S subunits, enabling them to become better ordered in the crystal. She then showed a diffraction pattern showing lots of spots. I couldn't believe what I was seeing and hearing. What I thought would be a quiet niche for me would now mean a head-to-head competition with Ada, and we weren't even sure we could get good crystals yet. I was in turmoil for the rest of the meeting. During a break, Steve White and I went for a walk in the nearby woods around the lake with Ada and Francois Franceschi, along with Isao Tanaka, a crystallographer from Japan, and I had to put on a good face the whole time. I mulled over the situation on what seemed like an interminably long plane ride back to Utah. I briefly considered just giving up, but then realized that Ada had obtained good crystals of the 50S subunit many years earlier, and she still hadn't solved it. Just because she now had good crystals of the 30S subunit didn't mean she'd suddenly figure out how to solve it either. The Yale group had shown that the heavy atom clusters were fine to get low-resolution maps, but as you get to high resolution, the heavy atoms in the cluster don't behave like a single superheavy atom. At finer detail, they look like a lot of separate atoms, and their signal drops. So my idea of using special atoms with synchrotrons to solve the structure using anomalous scattering still seemed to be the only way forward to get a high-resolution structure that would yield an atomic model of the ribosome. In the end, what really swayed me was the realization that the structure of the ribosome was the most important goal in my field. There seemed a narrow window of opportunity, and since I had a clear idea of how to attack the problem, it would be a mistake to be dissuaded by this new development. Furthermore, even if I wasn't one of the first groups to solve an atomic structure, the ribosome was such a complicated machine that understanding it would take lots of structures in different states of the process. There would be plenty of interesting work for years to come, and to be best positioned for that, I should get started sooner rather than later. Anyway, there was no time to lose. Instead of Yale, it was I who would be in direct competition with Ada's large, well-funded group. I felt I had to tell Richard of the new situation. Fortunately, he was not in the least bothered by it. He felt I had at least as good a shot as anyone, and thought the fact that I had solved many different structures was good experience for tackling a hard problem. But there was still no job offer. He said they were interested in my coming to the LMB to work on the ribosome, but they didn't have any space at the moment. However, they were expecting to acquire some, and when they did, they would get in touch. Given Ada's improved crystals, we could not afford to wait for the LMB. I told my lab about the meeting in Tallberg, and it was full steam ahead. We had to adopt a two-pronged strategy. The first was to continue to see where the crystals of the 30S would lead us. Perhaps we too might be able to stabilize them in some way, as Ada seemed to have done. The other was to try to lock them with IF3 and try to get crystals of that, which would also be more interesting because it would show the 30S in the act of doing something, like binding a protein, that is required to initiate translation. Fortunately, this idea didn't need to work, or I'd still be waiting. Our immediate task was to see how good the crystals we already had were. When I went to Brookhaven to collect data on a different project on Bob Sweep's beamline, I also took several frozen crystals of the 30S subunit. We decided to look at them on the adjacent beamline, which was more intense and would give us a better idea of their quality. It was run by my old friend and colleague, Malcolm Capel. Malcolm was a big guy with a large bushy beard and long hair that he wore in a ponytail. He had grown up in a Mormon family in Utah, but despite this fairly conservative upbringing, he was a highly irreverent and irreligious character who liked his beer and partying and peppering his language with swear words in new and creative ways. As the evening wore on at parties and the beer started to work, he would become incredibly witty, making hilarious and very frank remarks about everyone we knew, including those present. Because we had worked on the same neutron project at Yale, although some years apart, and we shared a connection through his wife, Sue Ellen Gertschman, who was my technician at Brookhaven, we had gone on to become good friends. I knew that Malcolm had an interest in ribosomes because of his background, and as an old friend and colleague, I implicitly trusted him. So I had told him about our project, and he said he'd help us in any way he could with his beamline. On my visit, we did test shots of lots of crystals on his beamline, and although they were a promising start, the spots did not extend out to high resolution. This was particularly disheartening, because just a little while earlier, I had encountered Nenad Ban, who had been collecting data on Bob Sweet's beamline before me. Nenad was an obviously intelligent and good-looking Croatian with a boyish face and engaging smile. He had done his PhD with Alex McPherson in California before joining Tom Steitz's lab as a postdoc. When he found out during his interview that Tom wanted to tackle the ribosome, Nenad was instantly excited because he had long been interested in it. He sometimes shows a drawing of the ribosome he made when he was still a schoolboy. Nenad told me that his biggest fear was not the challenges of working on this daunting problem, but rather that Tom might give away the project to someone else before he actually showed up some months later. When I arrived at Bob's beamline, the last diffraction image that Nenad had collected on their 50S crystals was still up on the screen, and my heart sank. Unlike our weak diffraction, it showed strong diffraction spots all the way to the edge of the detector, even on a relatively low-intensity beamline. Nenad's confidence was also intimidating. He was in a hurry to catch the ferry back to New Haven and asked if I would take out the tape that was backing up his data when he was finished. He didn't seem the slightest bit worried that I could take a sneak look at it. Soon afterwards, we learned that the Yale group had crossed the 10 angstrom resolution threshold. They eventually published a paper in Cell in which their maps showed the right-handed double helical twist of segments of the RNA. They rather pointedly mentioned that their map showed density features expected from other structural studies, and went on to say that the work constitutes an important beachhead for launching an attack on the structure of the ribosome at higher resolution. I was already worried about Peter and Tom being formidable rivals. Nenad, whom I had met, was obviously first-rate. I noticed that the author list included Poul Nissen, another top-notch young crystallographer who had joined them from Aarhus in Denmark after solving a very important and tricky structure on the complex that delivers amino acids to the ribosome, consisting of tRNA with its attached amino acid and a protein factor called EFTU. So Yale had assembled a crack team, while we didn't even have good crystals yet. Hopefully, they wouldn't figure out my idea of how to get to high resolution too quickly. We were falling further behind, but there was nothing to do but push on. To test our idea of locking the 30S subunit down by forming a complex with IF3, I contacted Joachim Frank about collaborating on doing a structure of it by electron microscopy. This would be a low-resolution structure, but since very little was known about how IF3 bound at all, it would be interesting in itself. It would also give us some feedback about whether the idea of locking the 30S was working. Importantly, now that the Yale group had used an electron microscopy map to get started with phasing their X-ray data, it might help us do the same with the 30S. At the time, Joachim wasn't aware that this was really a prelude to our attempting to crystallize the complex, but since just knowing roughly how IF3 bound to the 30S was interesting enough, he said yes, and had his postdoc, Raj Agrawal, collaborate with John McCutcheon on it. John soon made the appropriate complex and went off to Albany to work with Raj on doing an EM structure of IF3 complex. In the meantime, our crystals had grown larger. On the next trip to Brookhaven, they seemed to do a lot better on Malcolm's beamline. The best of them seemed to go to about 5 angstrom resolution. Close, but not quite there. Bob Sweet came by and said they had a new high-intensity beamline and asked if I'd like to try my crystals on it. I had nothing to lose, so I stuck a crystal on and nearly had a stroke. The crystal diffracted to beyond 4 angstrom resolution, with diffraction spots going out almost to the edge of the detector. The spots at high angles were quite weak, which is why we had needed a very intense beam to see them. But it meant the crystals were good after all, even without binding IF3, as I'd originally thought would be necessary, or stabilizing them with some, yet unknown to us, heavy atom cluster, as Ada had done. Perhaps all it had taken was to make sure the preparation was very pure and homogeneous, with the variable S1 protein removed, and possibly growing them very slowly over a period of weeks in the cold room at 4 degrees Celsius also helped produce better crystals. Whatever the reason, to our pleasant surprise, we had caught up with the other groups with our well-diffracting crystals. Now we had to figure out what to do with them. Chapter 10. A Return to Mecca. Some time after returning from Sweden, I got a phone call from Ada out of the blue. I had described our structure of S15 in Tolberg, and Ada asked if she could mention the results in a review she was writing. I thought this was an odd reason to call me. It could easily have been dealt with in an email. I told her that the structure was due to be published soon, and she could certainly cite it. Then, somewhat mischievously, I said, "Well, Ada, it was nice talking to you." "There is one other thing," she immediately replied, coming to the real reason for her phone call. She said she had heard we were working on the 30S subunit. I didn't want to have to discuss with her where we were and what we were doing, but I didn't want to lie outright either. So, in a Clintonian manner, Bill, not Hillary, I said, "We're thinking about it." After all, we were thinking about it, night and day. Ada added that they'd made great progress, and in her maps, she could now recognize the proteins whose structures we had already solved in isolation. If we had new ideas, she'd be happy to consider them. I politely told her that for now we wanted to give it a shot ourselves to see how far we could get with our own ideas. I didn't know this at the time, but Peter Moore recently told me that she had paid a surprise visit to Yale around then and offered to collaborate with them too. Collaborations work best when the people involved are good friends, enjoy working together, and have complete confidence in each other, or when they have complementary expertise that allows them to tackle something neither could do alone. They also require a willingness to give up complete control of the project and to share credit in ways that might not seem fair to all parties. At this point, neither I nor Yale were interested in collaborating with anyone else. Ada's call left me in a complete panic. Clearly, I had not been as discreet as I had thought. And what did she mean she could recognize our protein structures in her maps? If that was true, she was so far ahead of us that perhaps we shouldn't even bother. Distraught, I went down the hall to see my colleague, Chris Hill, who just laughed. He thought it was pretty unlikely that the first thing someone would do after obtaining great maps would be to call a potential competitor and tell him about them. I felt better, but the whole thing stressed me out because it brought home the reality of the competition that I had originally tried to avoid. Finally, Richard Henderson wrote, "The space had come through, and they were interested in proceeding with hiring me." I suddenly had to make what was one of the hardest decisions of my life. Whether to gamble everything on going to the LMB and work exclusively on this project. If I stayed in Utah, I'd have to hedge my bets by working on other safer projects simultaneously. But these projects would slow me down on the 30S. And now that the race was heating up, I felt I needed to focus on it completely. There was a narrow window of opportunity, and if I didn't grab it, I would watch other groups do it and regret it for the rest of my life. Vera and I enjoyed living in Utah, and many of my colleagues there had become good friends. For a while, I was torn. Then I decided to seek some advice from two people whom I particularly respected because they had tackled similar hard problems. The first was Peter Moore. I didn't tell him about the 30S project, but asked him whether he thought moving to the LMB was a good idea. He said Utah was a fine place, but the LMB was unique, and if I had a chance to go there, I should seriously consider it. The second was Steve Harrison from Harvard, who was one of the foremost structural biologists of his generation. He had burst onto the scene when quite young, tackling what seemed an impossible problem at the time, the structure of an entire virus, when computers were primitive and there were no synchrotrons. He also showed courage in his personal life, being unabashedly gay at a time when most people were afraid to come out of the closet. I doubt he ever imagined that one day he would be legally married to his longtime partner, Tommy Kirchhausen, a well-known cell biologist at Harvard. Steve was also famous for being brutally frank. He publicly characterized crystallization in space, an expensive effort to send protein solutions up to the space station to try to get better crystals under zero gravity, as a waste of time and money. He once began an advisory meeting at Brookhaven by roundly chastising the director of the synchrotron for presuming to tell biologists how to do their experiments. I felt that if there was anyone who would tell me bluntly that moving to the LMB to work on the ribosome was a bad idea, it was Steve. As it turned out, he didn't. Instead, he thought that the field would benefit from competition, and now that others like Tom and Peter had entered the race, there was no reason why I shouldn't. I should consider what the LMB could provide that Utah couldn't. I didn't know it at the time, but Steve is a good friend of Ada's, and it says something about his integrity and objectivity that he was so encouraging. Over the years, he went on to become a close friend of mine too. Because of his love of chamber music, he has even got to know and on occasion supported my son Raman, now a cellist. In the end, after a long walk with Vera, we made our decision. We would leave our families, including our grown children, in America and go to England, where I would take a large salary cut to stake all on the ribosome at the LMB. Vera had uncomplainingly followed me around the US throughout my career, even when I went across the country to go back to graduate school right after Raman was born. I was lucky that she was a self-employed artist and writer, but even so, each time she had to uproot her life and move away from her home and friends. She agreed to do it once more, if I felt it was important for my work. However, she said, it would be the last time. So far, she has kept her word. Dana Carroll, who had hired me just a few years earlier, was visibly shaken to hear the news. He made the prospective salary cut even more painful by immediately giving me a raise. But deep down he knew it was not going to matter. In the end, he, Wes, and Chris were wonderfully supportive, even after I had told them I was leaving. Rather than being angry, I got the sense they were rooting for me. In any case, since I'd committed to going to Cambridge to work on the ribosome, we needed to make as much progress as we could to make up for any time lost to the move. Brian Wimberley, who had initially been cautious about working on a very risky project for his second postdoc, had now solved two structures, including an important one of a ribosomal protein bound to a piece of RNA. At this point, his postdoc could be considered a success, and he too wholeheartedly threw himself into the 30S project. We now had to figure out how to obtain all the compounds we might need to produce an initial structure from the crystals. The first thing I did was go through the periodic table and get salts of every metal that would provide a strong anomalous signal at X-ray wavelengths that synchrotrons could produce. These were mostly the lanthanides, like holmium, ytterbium, europium, and so on. To use these elements to get phases and thus a map, you had to first locate where they were bound in the crystal. There were computational methods that should allow you to locate them directly, but they'd never been tried on a problem like this before. What if the signal from each of them was too weak? However, the Yale group had already shown that at least one heavy atom cluster could be seen directly in Patterson maps. Even though you would only get low-resolution phases from it, you could use those phases to locate where the other atoms, like the lanthanides, were. We were in a race now, and couldn't afford to try one thing at a time. Instead of first trying to see if directly locating the lanthanides would work, I felt I had to cover my bases. So, like Ada and later Tom and Peter, I too wrote to Michael Pope, an inorganic chemist at Georgetown University, and asked him if he could provide me some of his tungsten cluster compounds. He was very friendly and provided me with his entire series of compounds, which were inorganic molecules containing anywhere from 11 to a staggering 30 tungsten atoms. He may well have wondered at the sudden interest in his tungsten compounds from various crystallographers he'd probably never heard of. I was able to get tantalum bromide from Gunther Schneider in Stockholm, who had used them to solve a large protein complex. Science does indeed depend on the kindness of strangers. The strategy was clear. I could get low-resolution phases from one of these clusters, or from an electron microscopy map, as the Yale group had done. Then, if I used those to locate where the atoms with strong anomalous signals bound in the crystal, I'd be able to bootstrap my way to high-resolution phases and be off to the races. After all, my calculations had already shown that the signal ought to be strong enough. But these calculations assumed the kind of diffraction you'd get from a typical protein. The diffraction from the 30S was much weaker. So I realized I couldn't be sure it would work. You'd need to do the experiment and just hope that the data were good enough. I saw a better alternative when, around this time, a paper came out on the structure of the largest piece of RNA determined to date. It was part of the RNA molecule that Tom Cech had shown could cleave itself without the help of a protein enzyme, for which he had shared the Nobel Prize. Cech's postdoc, Jennifer Doudna, had started the project to determine its structure in his lab in Boulder, but then continued it at Yale when she joined its faculty. Jennifer was a brilliant scientist who had done her PhD with Jack Szostak at Harvard, where she worked on RNA catalysis. Following her postdoc with Cech, she went to Yale, where she had a remarkable series of successes and continued an illustrious career in Berkeley. In the last few years, she has taken the world by storm for her part in developing the CRISPR-Cas method of modifying genes, for which she has won numerous awards and probably will win the Nobel Prize. Unusually for a scientist, she was also once featured in Vogue. The graduate student who began working on the project with her in Colorado, Jeremy Cate, followed her to Yale. He did more than just follow her. They soon entered into a relationship and are now a star couple like Tom and Joan. The paper by Jamie and Jennifer had used the same MAD method I was thinking of for the 30S subunit, but in addition to the lanthanide metals that I was considering, they had hit on an even more magical bullet. It was a compound called osmium hexamine that nobody had used before for phasing crystal structures of large molecules. From the way it bound to their RNA molecule, I figured it would bind to the ribosome in dozens of places, unlike lanthanides, which might only bind in 10 or 20 sites at most, so it was likely to give a much better signal. Alas, it was not commercially available. The paper said they had obtained the compound from Henry Taub, a well-known inorganic chemist at Stanford. I wrote to Taub, but here my luck almost ran out. He wrote me a terse and somewhat irate letter saying he had run out of the material, and since his grant was terminated, he didn't have the resources to make any more. I, a theoretical physicist turned biologist, certainly didn't have the skills to make it myself. Fortunately, science depends on the kindness not only of strangers, but also of friends. The friend in this case was Bruce Brunchfig. Vera and I had got to know Bruce and his wife Karen over the dozen years at Brookhaven. From the moment I first met them soon after my arrival there, they struck me as people I'd want to know better. Bruce, who had grown up in Philadelphia, had an irreverent East Coast Jewish sense of humor that I particularly enjoyed. We became and remain very close friends, partly because we hit it off, and partly because our children grew up together and went to the same school. They lived a couple of blocks away, and we would often spend weekends together on outings where the main feature would be the long naps that Bruce and I would take after lunch. So, in desperation, I asked Bruce, a trained inorganic chemist, if he could make me some osmium hexamine. He took a look at the synthesis and said he probably could make it for me in a couple of weeks with the help of his technician. It is typical of his character that he declined to be a co-author on the papers that would make me well known, saying it was just a routine synthesis. Others have been authors for far less, and his help made the difference between success and failure. So finally, I had assembled the compounds that I thought we'd need to use with our crystals to get a structure. The collaboration with Joachim and Raj on the IF3 project was also proceeding well, and we would soon have electron microscopy maps of the 30S as well to perhaps use to get initial phases. With a steady supply of crystals being produced slowly in the cold room, we were ready to blast off. While all this was happening, I got yet another shock. One of my colleagues in Utah was Brenda Bass, who had made important discoveries about how mRNA was modified or edited. Soon after I had arrived in Utah, I found out she was in a relationship with Harry Noller, the biochemist who was well known for his work on ribosomal RNA. I remember being quite surprised, at least in part because Santa Cruz was not exactly next door, and thinking Harry was rather lucky to persuade someone like Brenda to enter into a long-distance relationship. However, I thought no more about it until, while attending a picnic at Brenda's place, I encountered Harry, who was visiting from Santa Cruz. We struck up a conversation, and he told me they were working on crystals of the ribosome. Crystals. How could Harry, a biochemist with no experience in crystallography, take on the entire ribosome? It turned out that he had hired Marat Yusupov and his wife Gulnara, who had been part of the team in Russia that had produced the first crystals of the whole ribosome from thermus. After their collaboration in Strasbourg had ended, they had been frustrated at being shut out of ribosome crystallography. So when Harry published a paper showing that he could reassemble the head of the 30S subunit from individual proteins and a piece of RNA, Marat wrote to Harry asking if he could come and work on the structure of this piece of the 30S subunit. Harry was not a guy to do things by halves, or thirds of a third of the whole ribosome in this case. The head of the 30S would tell you almost nothing about how the ribosome worked. Why not come and work on the entire ribosome? Marat and Gulnara were thrilled, and the couple went off to Santa Cruz to start working on the entire ribosome. Marat told me he suggested to Harry that they collaborate with someone well-known who had experience in solving hard structures. Instead, preferring to keep it in-house, Harry hired a young, ambitious postdoc, none other than Jamie Kate. Although I was in denial at first, I realized that Jamie, who was no fool, was one of the few people who would almost certainly see the exact same path to phasing data from ribosomes that I thought was my secret idea. With the Yusupovs producing crystals using their years of expertise starting in Russia, and Jamie's experience at solving a large RNA structure using exactly the method that would be useful for the ribosome, Harry had assembled the perfect team. I wasn't at all happy that, in less than a year, what I thought was a niche for myself had turned into a four-way race. For the rest of my stay in Utah, I could not help being paranoid about discussing the ribosome project with Brenda. This was a pity, because she was someone I admired, with whom I shared a lot of scientific interests. Soon after the decision to move to Cambridge, John McCutcheon came to see me with an embarrassed look. After initially being very enthusiastic about the move, he said he couldn't go after all. He was now in a relationship with a fellow grad student, and it would be too complicated. The technician, Joanna May, also had a family and was not moving. Suddenly, my already small group was going to be half its size as a result of moving. I went to the annual Students' Day at the LMB in the hope of persuading a grad student or two to join the effort. One of them, a well-qualified German, listened to my pitch and said, "There's a large group in Germany that has been trying to do this for 20 years. What makes you think you'll succeed?" I tried to tell him that even if we didn't succeed right away and got scooped on the first structures, there would still be plenty of work left for us to understand the ribosome. Almost right after our interview, he signed on with Kiyoshi Nagai, my friend and future lab neighbor. A couple of other students, including one from Cambridge, seemed to be completely clueless about the problem. I thought they'd only slow us down. Despondent, I spent the flight home wondering whether I was shooting myself in the foot by moving. Shortly after my return, I wrote to Tony Crowther at the LMB saying that I was rethinking the whole move. Fortunately, in the next few weeks, 2 people courageously agreed to join my lab at the LMB without ever having met me. Andrew Carter, who joined me from Oxford as a PhD student, and Ditlev Brodersen, a postdoc who came highly recommended to me from Aarhus in Denmark, where I knew his supervisor, Morten Jelgaard. As I was to find out, I cannot have had 2 people who complemented Bill and Brian more perfectly. Their joining me was a stroke of luck and meant we would have a viable team at the LMB. Moving to a new lab always costs time, and moving to a different continent in the middle of a race seemed insane even to me. So I wanted to make sure that we gave ourselves a good head start. We had electron microscopy maps of the 30S subunit from Joachim as a result of the IF3 project. However, I failed to locate the 30S in our crystal using these maps with the X-ray data. Perhaps the maps were at too low a resolution, and perhaps the 30S was too thin and flat an object. But since the Yale group had shown you could directly see heavy atom clusters in a Patterson map, trying to use electron microscopy to get started wasn't actually necessary, even to get low-resolution phases. So Bill ended up soaking dozens of crystals in each of the many compounds I'd accumulated, and with Brian, in early March 1999, we were off to the synchrotron at Brookhaven to see what we could get with them. Unlike Ada's unusual observation of a heavy atom cluster actually improving diffraction, our best diffraction was still from the native crystal, to which we hadn't bound anything. As is much more typical, the crystals soaked in the various compounds all diffracted worse to varying degrees. We had chosen the wavelength of the X-rays to maximize the anomalous scattering from the heavy atoms, and thus increase the small differences in the intensities of the symmetry-related spots. Those differences contain the signal from the heavy atoms, and a Patterson map using the differences would produce a peak showing where the heavy atoms were. As the data were being collected, we processed them on the fly and calculated one Patterson map after another. Nothing seemed to be working, and I was slowly getting exhausted and depressed. Then, after midnight, a Patterson map from a crystal soaked with a 17-atom tungsten cluster showed 2 large, unmistakable peaks. Brian and I looked at each other and instantly leapt out of our chairs and did a high five with a huge shout, startling a lone physicist who happened to be nearby. We quickly did some additional experiments on the same crystal to confirm the peaks, and when we saw them again, there was no doubt at all. We returned to Utah euphoric. Soon afterwards, a low-resolution map calculated from just the 17-atom cluster clearly showed an outline of the 30S subunit and how it was packed in the crystal. We had our foot in the door. Maddeningly, Only a month after having made this exciting breakthrough, it was time for me to leave Utah. Bill and Brian were to continue working there with Joanna for a few months, help close up the lab, and then follow me to England. Having sold our house, Vera and I took a flight for London on April 15th, 1999. Chapter 11. Coming Out of the Closet. It's one thing to visit a foreign country for a year, and quite another to burn your bridges and move there. All countries have their peculiarities, but we become used to our own, whereas those of other countries strike us as strange. So in America, I had become used to the idea that lots of otherwise reasonable people own guns for no good reason, public transport is virtually non-existent in most places, and many people live in suburban sprawls and drive everywhere. During our sabbatical in England, we had noticed things like rigid bureaucratic rules administered with an earnest smugness, queues for almost anything forming in ways that were impenetrable to foreigners, so you were never actually in line, customer service that was an oxymoron, or, my favorite, locals feeling that "we've always done it that way" was a perfectly reasonable response when questioned about some completely silly practice. But things that had seemed charming and quaint, if a little odd, during our sabbatical, were annoying when they became a permanent part of our lives. We had sold our 5-bedroom house overlooking the Salt Lake Valley and the Wasatch Mountain Range, and were renting a place owned by the MRC. From the very first week, we started looking to buy a house. Before committing to the job, I had inquired what a modest terraced house would cost in Cambridge, and figured we could just about afford one. Between the decision and the move, prices had risen by almost 50%, and were continuing to rise almost weekly. For a while, we were outbid on virtually every house, and our inability to buy anything at all added to Vera's unhappiness about leaving her friends and nice home in Utah. It probably didn't help that right from the start, I had a near obsessive focus on the 30S structure. Normally, a move would have slowed us down considerably, but for a couple of reasons, we may actually have speeded up our progress instead. Since we'd collected the data we needed for this phase of the work, I could not have moved at a better time because the LMB had excellent computing facilities. This meant that I could speed up the work by trying lots of calculations in parallel, see what worked, and then use that as a guide to do the next set of calculations. It turned out that virtually every compound Bill had soaked into the 30S crystals was useful. The 17-atom tungsten cluster was the only one whose signal was large enough to see directly as peaks in sections of the Patterson maps. But although it wasn't obvious from a direct inspection of the Patterson maps, all the other compounds had also bound to the 30S subunit. When the signal is weaker, there are programs that can find the heavy atoms in a nearly automatic way. One of them was a program called Solve, written by Tom Terwilliger from Los Alamos. Tom is one of a small group of brilliant computational crystallographers, the people who write the software that everyone uses. He is a cheerful guy with a great sense of humor who works at Los Alamos National Lab, where his wife is a ranger in the Santa Fe National Forest nearby. I had used his program when I'd done a comparison of various ways to solve MAD structures. His program was as good as any of the others and was by far the easiest to use. He had written Solve to try to automate the problem of not only finding the heavy atom derivatives, but also using them to calculate phases and produce the electron density maps, the three-dimensional images. Brian started using Solve with our 30S data, and by the time I'd settled into the lab in Cambridge, he found that Solve had identified peaks for heavy atom positions in every compound Bill had soaked into the 30S crystals. This included all the other clusters and the various lanthanides and osmium hexamine. Initially, the program would identify only the strongest peaks, but by combining the data, it would slowly bring out some of the weaker ones. Combining them wasn't so straightforward because, as is often the case, adding a heavy atom compound would change the crystals themselves. They were no longer isomorphous, which is to say the 30S subunits in the crystals had themselves changed slightly as a result of binding the compound. So it was not possible to combine the data from different crystals easily. We had about 15 or 20 datasets, and we needed to figure out the combination that would give us the best maps. Being at the LMB, with its multiple computers nodes, was especially helpful, because I could now try lots of different combinations in parallel and compare the various maps. Another odd advantage of my move was the time difference between Cambridge and Utah. I would set up a number of computing jobs and, at the end of each day, I would email the results to Utah, which was 7 hours behind. Brian and Bill would look at the maps during their day and tell me what things were working and what weren't. So when I came in the next morning, I'd have my feedback. This effectively extended our working day by about 7 hours, so we were working almost around the clock. Slowly, the molecule appeared before our eyes. Initially, we could see its broad outlines, where the molecule was and where it touched neighboring molecules in the crystal lattice. Then its detailed shape began to appear. As the maps improved, we were able to find even weaker sites, ones that Solve couldn't identify automatically, and throwing them into the calculations made the maps even better. Suddenly, a month after I had arrived in Cambridge, there it was. A long RNA double helix that ran right down the face of the 30S subunit. Unusually for me, it was fairly late, and I rushed out of the graphics room in the LMD and found Richard Henderson, who was famous for working late into the night. He agreed it looked like a double helix. Excitedly, I sent it off to Utah. I almost wished I could have been there when they saw it. Brian very quickly identified the outlines of the 30S and its characteristic shape in the map. He then went on to find lots of other double helical regions of RNA. We knew that the RNA in the 30S formed around 40 of these helices, although some of them were quite short, unlike the long helix, number 44 or H44, that we'd first seen. RNA helices are A-form, which is named after the dehydrated form of DNA that Rosalind Franklin first observed, unlike the more typical B-form of normal DNA that she saw when DNA was hydrated. We could easily see the narrow but deep major groove and the wide but shallow minor groove that characterize these A-form helices. Our best maps were at around 5.5 angstrom resolution, which meant we could even see phosphate groups as a series of bumps along a ridge as we followed the helical turn of RNA. Our strategy was working beyond our expectations. At this point, my colleague Daniela Rhodes suggested that we should report our results in Nature. Daniela is well known for her work on chromatin, but she was also the person who over 2 decades earlier had done important work on tRNA with Aaron Klug and Brian Clark. We had become good friends during my sabbatical, and she had been strongly supportive of my move to Cambridge. She told an editor at Nature about our results, and he got in touch to say he was very interested in publishing them. We thought a short report describing our progress would be a good way of staking our turf. These short reports in Nature are called letters, for historical reasons, as opposed to articles, which are longer and more substantial papers. But longer is not always better or more important. One of the most famous papers in Nature, the Watson and Crick description of the double helical structure of DNA, is an amazingly short letter of only about 800 words. But something seemed wrong with our maps. We could see a lot of RNA in them, but there seemed to be no sign of proteins. They had to be there, since there were about 20 of them in the 30S subunit. Maybe because they are not as dense as the RNA, they weren't showing up in our maps. I was puzzling over this when I noticed that some of the density looked like tubes that were a lot thinner than the RNA double helices. In fact, they seemed the right size to be alpha helices that proteins often form. And in a few places the tubes packed against each other in the way that these helices do in proteins. I wrote to Brian and told him what I'd seen, and went to bed. I was not prepared for the surprise that awaited me when I went into work the next morning. Of course, I had expected the usual emails from Utah telling me what had gone on while I was sleeping. But that morning, there were several emails from Brian. The first was telling me that, yes, he could see that we had missed the density for proteins, and he'd identified one of them, S6. At the resolution we had obtained, we couldn't build a new protein from scratch, but if a structure was already known, we could place it in the map so it roughly fitted into the density. Anders Lilius had collaborated with Maria Garber to solve the structure of S6 by itself. Proteins typically consist of structural elements like alpha helices, which should look like tubes at this resolution, and extended beta strands that go back and forth to form a flat sheet. Brian could take the atomic structure of S6 and place it in the density in the 30S by simply aligning where the tube-like helices and the flat beta sheet went. For the first time, we could see directly where a protein was in the 30S and how it was interacting with the RNA. It was like knowing in detail what an isolated steering wheel looks like, and then for the first time realizing where it belongs in a fuzzy image of an entire car. But that wasn't all. Over the course of a single night, Brian had located one protein after another, until he had located all 7 previously known protein structures in the 30S maps. Actually, although he knew where it was, he had left S5 for me to place, since he knew it was the first protein structure I had ever solved and had a particular affection for it. Placing a protein in the 30S subunit had been so exciting that Brian said it was like eating crisps. Once he did the first one, he couldn't stop. A lot of parts were now being placed into the fuzzy picture of the assembled machine. Initially, when we saw an RNA helix, we didn't know which part of the ribosomal RNA it was. With several proteins in place, it became possible to identify the pieces of RNA next to them because there were lots of biochemical data from people like Harry and Richard Brimacombe to show which proteins were near which pieces of RNA. Luckily, Brian had a lot of the data in his head or remembered where he could find it. So pretty soon, he had identified the segment of RNA near S6 and worked outward from there until he could see how an entire section of RNA, called the central domain, was folded. This was a much bigger breakthrough than we had ever dreamed of at this stage. We were seeing the molecular architecture of about a third of the 30S subunit, with the proteins and RNA all connected with each other to form an intricate complex structure. Looks like an article, not a letter, was Brian's verdict. Indeed, we had to start writing up our results right away. The breakthrough came not a moment too soon. The next ribosome meeting was being held just north of Copenhagen in June, only a month later. When I contacted them before their deadline while I was still in Utah, we didn't have anything concrete, but we knew we had good crystals and were about to collect some data. In the worst case, I could simply say we'd entered the fray and had made some progress. On that basis, I asked one of the organizers, Roger Garrett, if I could give a short talk. The abstract or summary I submitted was a vague one-liner saying we'd report our progress on the structure of the 30S subunit. It said absolutely nothing beyond the equally vague title. Despite my vagueness, Garrett generously tacked me onto the end of the opening night session on the structures of the entire ribosome or its subunits. He later told me that when the conference committee met, Peter Moore was doubtful that we had anything substantive since he had just seen me at Brookhaven a couple of months earlier, just before we began collecting our data. That was true. I didn't have anything then. But Garrett said he wanted to take a chance and include me because he somehow got the feeling I had something up my sleeve. We never imagined our progress would have been so rapid. The next few weeks were a frantic effort to make sense of our results and write a coherent story for Nature. We wanted to send our paper off before I went public, because once word was out, there would be a mad scramble with everyone trying to get their papers out. This is where being a part was not so helpful. In cases like this, different people are doing complementary tasks, like making figures or writing different sections. They often have different schedules and don't always see the others doing their work. With the stress of a deadline, each often feels the others aren't pulling their weight and tempers fray. Normally I'd nip these tensions in the bud, but I wasn't there and had to calm everyone down over long distance. Somehow, we got the manuscript written, and I mailed 3 hard copies off to Nature just before setting off for Denmark. The train from Copenhagen Airport to the quaint small city of Helsingør took about an hour. Just across the strait from Sweden, its English name is Elsinore, of Hamlet fame, and the plays perform there every year. Steve White and I were sharing a room. I had told Steve a long time earlier about our efforts to start working on the 30S. Like many others, he had been somewhat skeptical about the enterprise. When we had located the 7 proteins in the 30S maps, I realized I had to let him know right away, because he would be talking about their structures in isolation. This meant that his talk on our work on individual proteins would come across as rather anticlimactic. So I had called him and let him know. But that was before we had solved the architecture of an entire domain of the 30S subunit, showing how the RNA was folded and how the proteins bound to it. When we met in Denmark, I told him the full extent of our work, and he seemed a bit shocked by our progress. But ever the gentleman, he was gracious about it. Not everyone would be. Most of the participants dribbled in during the afternoon, and there was to be an opening session just before dinner. The speakers were Tom, Ada, Jamie, and me, in that order. Except for a very few people, this was to be the first time anyone had any inkling that I was working on the entire 30S subunit. Suddenly, I was more nervous than I had been in years. The talk began with Tom describing how they had made progress on the 50S structure. They were now at a similar resolution as we were, and could see similar features in their RNA and proteins. They had also identified a few proteins and elements of RNA. After his talk, Ada got up and tried to make the point that he shouldn't be seeing proteins at all because the crystals of the 50S subunit were grown in high salt. Her point was that the electron density of a concentrated salt solution would be so high that the proteins would have very little contrast and shouldn't be visible. Tom disagreed with her, and she persisted. Finally, he lost his patience, folded his arms and said, "I've solved lots of structures in 3 molar ammonium sulfate. How many structures have you solved?" There was an awkward silence, and that was the end of the discussion. Ada then got up to speak. She reported progress on her new 30S crystals and showed maps, including a couple of proteins. But unlike Tom's maps, we weren't shown the sort of clear features and overall shape that suggested that there had been a breakthrough. Next, Jamie Kate got up to speak about their progress on the entire ribosome. Given his history, I had expected he would use osmium hexamine to phase the data using MAD. Actually, he had used the very similar iridium hexamine, which he told me later was a lot easier to make. The maps were at about 7.8 angstrom resolution. This meant he couldn't see the architecture of proteins that the Yale or OWL groups could, but he very clearly showed the grooves of the RNA double helices, including the long helix we saw running down the face of the 30S. The most interesting thing in his talk was that we could see the shapes of 3 tRNAs nestled in between the 2 subunits and the entire ribosome in greater detail than ever seen before. Then it was my turn. I started off by saying how we had managed to get crystals of the 30S subunit that diffracted well without having to stabilize it in any compounds, simply by carefully purifying it and removing a protein component that was only partially bound, so the 30S subunits were homogeneous. Then I described our progress in getting maps we could make sense of. I said that letting Brian have a crack at these maps was like giving a teenager the keys to a Ferrari, a remark that was later quoted in Science, leading his mother to call him Ferrari Boy. I had seen Harry sitting in the front row, and this was also a dig at his fondness for Ferraris. Finally, I talked about how Brian had figured out the architecture of an entire domain. There was complete silence after my talk, before Anders Lelius, who chaired the session and must have been taken aback by our unexpected foray, asked me how long we had been working on it. Ada asked me how we phased the structure. I didn't want to give too much away because the structures were far from being done, but I gave her a general outline of the heavy atom clusters and other compounds we had used. This reticence was foolishly paranoid, since Jamie had already gone public with their strategy, which was identical to ours. But it is hard to change one's mindset, and I still had the mentality of someone trying to catch up from behind. There were a few more questions, and then it was over. We had not only caught up with the field, but had also, at least temporarily, built more of the ribosome than any other group. There was a huge buzz in the room as people started talking animatedly on their way to the dining hall. It was immediately clear to everyone that, after 40 years, the ribosome field was about to change dramatically. Lots of people complimented us on our work, and Tom was congratulatory, but seemed a bit rueful that I hadn't let on anything at all, even just before the talk. Peter seemed proud of his protege. Harry looked very thoughtful and also very surprised at our apparently having come out of nowhere. Not everyone was happy. Many biochemists, who were trying to get at structure using biochemical tools, suddenly realized their way of life was about to end. The foremost of these was Richard Ribosome, who, like Harry, had been one of the few ribosome biochemists to dedicate much of his life to working on the RNA part of the ribosome. An Englishman who had spent most of his career at Wittmann's Institute in Berlin, he had become interested in the problem of translation when working on the genetic code with Marshall Nierenberg in the 1960s. More recently, his idea was to combine the painstakingly obtained biochemical data that he, Harry, and others had generated on roughly which proteins were near which piece of ribosomal RNA with low-resolution blobby images that were being generated by electron microscopy. The electron microscopy maps he was working with were generated by Joachim Frank's rival, Maren van Heel. The problem was that the data were not precise and the images not sufficiently detailed to recognize features unambiguously. Still, for a while, it seemed as though this would be the only way to get some sort of approximate molecular model of the ribosome. Oddly, he got closer to the truth with the more complicated and much bigger 50S subunit than with the 30S. But after that night's session, he could see that he was soon going to be steamrolled by progress towards a high-resolution structure of the ribosome. It could not have been easy for him to give his talk later in the meeting. Peter Moore could sense the anxiety on the part of many in his meeting. In his summing up remarks that marked its close, he tried to assuage their fears by paraphrasing Churchill. This is not the end. It is not even the beginning of the end, but it may be the end of the beginning. Certainly for those biochemists who were focusing on how the ribosome worked rather than what it looked like, that turned out to be true. It could not have been easy for Ada, who had started the crystallographic work about 2 decades earlier, to suddenly see others making such rapid progress and overtaking her. I heard from several people at the meeting that she was less than charitable about Tom and me. I could see how she might feel about the turf she had so long occupied by herself suddenly being invaded from all sides. So when it came time to contribute a chapter to the book on the conference, I thought it would be appropriate to start it off with a description of her breakthrough on the 50S crystals and how that pioneering work had paved the way for what came later. It turned out to be the opening paragraph in the opening chapter in the book. But if I'd naively expected that this homage would mollify Ada and lead to peace and goodwill all around, I was soon disappointed. The next couple of years turned out to be a period of fierce and acrimonious competition. No matter how amazing they seemed, the results so far, even from the Yale group and us, were only progress reports, and what we could do with the maps at this stage was limited. If we already knew the structure of an isolated protein, we could place it into the maps, but the resolution was not good enough to build those parts of the ribosome for which there was no prior information. So we could not really figure out the structure of something completely unknown. Moreover, even the models for the parts we could construct were only approximate. They could tell us the rough architecture, but not the detailed and accurate atomic structure that would allow us to understand its chemical mechanism. Now that we had shown that the crystallography was working, it would be a flat-out race to get data to better than 3.5 angstrom resolution and then build a complete atomic model of each subunit. To Peter, this seemed inevitable. At the conference, I met Ditlev Brodersen, who had agreed to join my lab. I introduced him to Peter and said he was going to join my lab as a postdoc. Peter wryly asked him if he was good with ribbons, which, at the time, was the leading computer program to display structures of proteins and RNA. He was joking that the structure would be done so quickly that all that would be left for Ditlev to do would be to make the figures for the paper. Unfortunately for us, it turned out not to be the case, although Ditlev turned out to be a master of lots of skills, including ribbons. Chapter 12. Almost Missing the Boat. Brian and I returned from Denmark ecstatic. Soon afterwards, a conference on nucleic acids was held in America. Neither the Yale group nor I were there, but Harry was. Brian, who went to the meeting to speak about our work, gave me an entertaining account of the proceedings. Harry was the subject of a great deal of adulation. There was already a lot of speculation about an eventual Nobel Prize for the ribosome. One young woman at the meeting asked Harry if he would take her to Stockholm with him and had him autograph her badge. Brian also told me that during a meal, Harry said, "The trouble with Venki is that he hasn't been doing this long enough." Long enough for what? To be considered one of the leaders? I thought it was a curious comment considering I'd been working on ribosomes ever since I was a postdoc, or over 20 years at that point. It was clear that even before the structure was actually solved, politics had begun to infect the race. Our submission to Nature was sent to the usual 3 anonymous reviewers. One of them was Steve Harrison, who was excited enough about the manuscript that he not only gave us detailed suggestions on how to improve it, but disclosed his name. Some of his comments were a little paternalistic, like crossing out a paragraph where we described the reasons for the breakthrough, saying, "Don't brag." Perhaps we had got a little carried away with our own success. Word had got around at the Denmark meeting that we had already submitted a paper to Nature on our results. Exactly as I had anticipated, this set off a mad scramble from the other labs to get their stories out around the same time. Soon afterwards, the Yale group submitted their story on the 50S to Nature also. The journal held ours so that the two could appear together. Although I was initially annoyed not to have our special unshared moment in the sun, in hindsight, the 2 papers made a nice pair, one on each subunit. The papers made something of a splash, with news items about them in several journals. Harry too got busy, and soon afterwards submitted his paper on the entire 70S ribosome to Science. It isn't just scientists who are competitive, but journals are too. Science published his paper rather quickly, with a great deal of fanfare, including an accompanying piece on the ribosome race by a journalist, Elizabeth Panizzi. She had written a short piece on our Nature papers only a month earlier, in which she had mentioned Ada and Harry mainly in passing. This time she wanted to do a longer piece, and started talking to various people. I suggested that if she wanted to talk to someone outside the ribosome field who was respected, she could talk to Steve Harrison. Steve, however, thought Panizzi's treatment of Ada in her earlier piece was dismissive, and refused to talk to her further, saying she should talk to Ken Holmes, a famous biophysicist at a Max Planck Institute in Heidelberg. Ken had changed the world of biological structures forever by showing that the intense X-rays produced by synchrotrons, which were used mainly for high-energy particle physics, could be used for diffraction studies. He and Gerd Rosenbaum, who, when I met him a year later, struck me as a brilliant, if somewhat opinionated and eccentric specialist in X-ray optics and instrumentation, built the first X-ray diffraction beamline at the DESI synchrotron in Hamburg. This was the same synchrotron outside which the Max Planck Society had conveniently built a lab for Ada, and where she had collected much of her early data. Having watched Ada work on the problem for years, he was not entirely charitable to us. "She's done most of the back-breaking work," he was quoted as saying. "The others have jumped the gun. They should have left Ada in peace." I was shocked and dismayed. It confirmed my worst fears of how some would perceive our efforts. Luckily for us, most people were happy about the breakthroughs and very supportive. And just 2 years later, when I first had the chance to meet Ken in person, he was very friendly and complimentary about our work, and we have remained on good terms ever since. Panizzi's piece also quoted Joachim Frank, referring to me as the dark horse of the Denmark meeting. He had meant to be complimentary, implying I had come out of nowhere and surprised everyone. But coming in the same report as Ken's remarks, and not long after I'd heard about Harry's comments, I found myself irrationally annoyed by it, seeing it as yet another effort to belittle me as a Johnny-come-lately. Of course, since I had deliberately kept our efforts very quiet, because we were starting out from behind, I could hardly complain about the dark horse description. But it caused a lot of ribbing by my colleagues, including some joking references to my dark skin. One friend superimposed a picture of my face onto the head of a black horse, and said I could use it as a logo in the slides of my talks. Another idea was to shrink it down to the size of a dot on the corner of the slide and have it gradually grow in size as the slides progressed, so that it would become obvious as a horse's head only towards the end of the talk. An homage to the famous scene of Omar Sharif's entrance in David Lean's Lawrence of Arabia. Suddenly being thrust into the scientific limelight was a new and uncomfortable position for me. It was also a distraction I could not afford. The real deal, the complete atomic structure, was still ahead of us. Getting the first atomic structure of a ribosomal subunit would now be a flat-out race between Yale and us, or so I thought. After all, The 70S crystals were not of sufficient quality to yield an atomic structure, and Ada seemed to have been left behind. In any case, it was time to get back to work. We needed new crystals and high-resolution data. The rest of the lab flew out to Brookhaven from Utah with more crystals, and I joined them from England. Now that we knew which compounds were going to be the most useful, we thought we could focus on just those to collect more data that might give us higher resolution. But even with this focused strategy, our trip led to almost no improvement over our previous maps. It was memorable mainly for my accidentally locking us out of both rental cars at a shopping mall in Shirley, just south of the lab at Brookhaven, and having to wait a couple of hours for the company to rescue us. Clearly, we needed to start again in England. While I was away at Brookhaven, Vera had found and successfully bid on a house in Grantchester, a picturesque and historic village just 3 miles west of the lab, so at least I could stop worrying about housing and concentrate on work. At the LMB, I was given 4 lab benches in a room that used to be Aaron Klug's old lab. It was the same room in which I had spent my sabbatical with Wes Sundquist, and many of its previous occupants had gone on to fame and glory. That history weighed heavily on me as I began to set up my lab for the autumn, when everyone would arrive. I advertised for a technician and gave the job to Rob Morganwarren, an earnest and muscular young man who had a black belt in martial arts and had just graduated from Birmingham. He and Andrew Carter were the first to arrive, and I took them through the basics of making ribosomes. Andrew and I had to figure out how to use a new chromatographic system, and he soon took charge of it. Around this time, Bill arrived from Utah and met Andrew and Rob. The contrast between Bill and Andrew could not have been greater. Andrew was from an academic family and had gone to Winchester, the oldest public school in the country, public in the British sense, meaning not public at all but very private. From there, he had gone to Oxford to study biochemistry, and then come to the LMB to start his PhD. Not only was his elite education quite different from Bill's, but so were their interests and personalities. Although Bill was an experienced senior graduate student with a track record behind him, Andrew was intellectually very confident and not the sort who would kowtow to Bill, or anyone else for that matter. Bright people tend to have strong personalities. With Bill, Brian, and Andrew, I could see that making sure the people in my team got along and worked together would be almost as hard as solving the 30S subunit. Brian's summer was exciting scientifically, but tumultuous personally, having gone through a divorce right in the middle of it. He briefly wondered at one point whether he should even join me in Cambridge. In fact, both Bill and Brian had done enough in Utah to finish up and move on to the next phase of their careers, so it was a very good thing for me that they decided to move to Cambridge to help finish the 30S structure. I was relieved when Brian finally showed up, looking a bit tired and worn by the events of the summer, but ready for the next phase. The last to arrive was Ditlev Brodersen. I had met him briefly in Denmark, but the meeting had been so hectic that we had not had a lot of time to chat. He turned out to be not just smart, but versatile, superb at everything from computing to lab work. He was also friendly, pleasant, and good-humored, traits that would be sorely tested in the next year. With the team in Cambridge assembled, it was time to get cracking again and produce more crystals. It is the nightmare of every crystallographer that moving to a different lab and using different sources for chemicals, or even a small change in the temperature of the cold room, could suddenly mean that nothing works. Fortunately, we were able to reproduce decent crystals, which Bill and I took to Brookhaven. But again, there was little improvement. A serious difficulty was that compared to the 50S crystals, the diffraction spots from our 30S crystals at the high angles that we needed to get to high resolution were very weak. To make matters worse, the beam line at Brookhaven spread out these high angle spots over a larger area, making their intensities even harder to measure. To measure the weak data accurately, we had to expose our crystals much longer. This meant that even at the low temperatures used for crystallography, the crystals still suffered damage while we collected the data, and we could not improve the resolution much. We had reached the limit of what we could do at Brookhaven. Closer to home, the LMB had routine access to 2 synchrotrons, an old one in Daresbury in the north of England, and a newer, much more intense one, the European Synchrotron Radiation Facility, or ESRF, in Grenoble, France. We quickly figured out that we could not collect any better data at Daresbury, but the synchrotron turned out to be very useful for checking the quality of our crystals. The one in ESRF was potentially great. It was a relatively new beamline and was going through teething problems, but that was not the most serious issue. The high intensity on the Grenoble beamline meant the crystals died even faster. This meant we would need lots of crystals to get a complete set of data from each of our heavy atom derivatives, and if we wanted to do an MAD experiment, we would need not one, but 3 complete data sets from each soaked compound. Moreover, the crystals were quite variable. Not all of them diffracted well enough to collect high-resolution data, and we didn't quite understand why. Even for the ones that diffracted well, the repeat distance or unit cell was slightly different from one crystal to the next. We were stuck. We couldn't collect high-resolution data from just one crystal because it would be damaged long before we could collect a complete dataset from it. Because the crystals were so variable, we couldn't combine partial data from lots of crystals to generate a complete high-resolution dataset. This meant that we would not be able to improve on the resolution we had. My euphoria from Denmark vanished. For the next few months, I was obsessively focused on finding a way out of our predicament. So much so that one day I found that Bill had made a flowchart and pinned it on the door of the lab. It was titled, Venki's Thought Patterns, January 2000, with a picture of a dark horse in the right corner. To their credit, Bill and Ditlev were willing to try all sorts of new ideas to get around the problem. Radiation damage is still not entirely well understood, but essentially, 2 types of damage occur, primary and secondary. We can do nothing about primary damage, in which a bond is broken due to an X-ray knocking an electron out of its orbit. But I thought we could try to minimize secondary damage, in which some of the damage to molecules generates highly reactive free radicals that diffuse and cause further harm. My knowledge of hardcore chemistry was pretty minimal, and I frantically thought of compounds to add to our crystals that might scavenge free radicals before they damaged our ribosomes. Ditlev tried a few like ascorbic acid, vitamin C, but none of them worked. If we couldn't slow down radiation damage, perhaps we could make the crystals more uniform so that we could use lots of crystals, each yielding a small fraction of the data before it was too damaged. This led to a crazy idea. What if the crystals had all started out the same, but variable rates of freezing meant they expanded or contracted to different degrees and ended up different from each other? By now, Bill had developed a routine for the incredibly tedious and unpleasant job of freezing lots of crystals in the cold room. He would put on his jacket and go into the cold room, get all his equipment set up, then set up a mini stereo system, put on his favorite Johnny Cash CD, and, for the next several hours, with hardly a break, manually fish out one crystal after another with a loop attached to the end of a pin protruding from a magnetic metal base, and then plunge them quickly into liquid nitrogen and store them in vials. Rob would be his assistant throughout the process. After a session like this, they would have dozens of vials filled with liquid nitrogen, each with a crystal in its loop. The vials would be slotted into metal canes that could hold 4 or 5 crystals, which would all be stored in a dewar, a vacuum flask, containing liquid nitrogen, waiting to be shipped off to a synchrotron. Even though this was done mostly by one person, Bill, maybe the process was too variable. When my colleague Phil Evans heard about my problem, he showed me a device that worked a little bit like a guillotine. After fishing out the crystal from the drop, you attached the assembly with the loop containing the crystal pointing downward to the top of the guillotine, below which was a little container of liquid nitrogen. As soon as you pressed a pedal, the guillotine would drop, so the crystals would all be plunged into the liquid nitrogen at exactly the same speed and perfectly vertically every time. Bill agreed that this might be the answer to our problems. If this idea worked, it would get us over the hump. With his usual enthusiasm about trying anything new, Bill took a couple of hundred of the best crystals that had taken about 8 weeks to grow, soaked them in the various heavy atom compounds, and used the guillotine to freeze them all. Over the weekend, Bill and the team took the crystals to the Daresbury synchrotron. That Sunday morning, I got a phone call from Bill. "You know, boss," he began. He always ironically called me boss. "The French Revolution was not a good thing." I had absolutely no idea what he was talking about. It turned out that the guillotine had never been used for freezing crystals. It was actually a device for plunging grids for electron microscopy. So each time Bill had used it to freeze a crystal, the guillotine had plunged down and stopped with a thud, and the crystal had shot out of its loop to disappear forever into the container of liquid nitrogen. Virtually every single loop they had looked at was empty, except for one in which the crystal had been frozen just before it could detach from the loop. With the loop looking like a hand, the long crystal protruding from it looked like it was giving Bill the finger. We had just lost 200 of our best crystals. More importantly, since the crystals took so long to grow, we had set ourselves back by at least 2 months in the middle of a tight race, all because neither Bill nor I had thought it would be worth checking the guillotine device out with a couple of crystals first, before trying it with all of them. I spent the rest of the weekend in a state of shock. But there was nothing to do but start again with the arduous job of making more 30S subunits and crystallizing them. While we were waiting for more crystals to materialize, I also realized that even if we got lots of matching crystals, we would still have a problem. Our whole strategy for obtaining phasors depended on anomalous scattering from special atoms like osmium, which gave rise to a small difference in intensity between symmetry-related spots called Friedel pairs. To calculate a structure, we had to measure those small differences very accurately. If we collected data on crystals that were not precisely lined up symmetrically with respect to the beam, the two spots in the pair would be measured at different times, so one spot would have suffered more or less radiation damage, and we would have to apply a correction. Or, since our crystals only lasted a short time in the beam, the two spots might often be measured on different crystals, and since the crystals varied in size and shape, we would have to correct the data from each to put them on a common scale. Either way, the errors in the corrections could themselves be much larger than the small differences we were trying to measure. A way to get around this problem is to line up a crystal very precisely along one of its axes of symmetry so that the diffraction pattern would look symmetric, with the pattern on the left side of the detector looking like a mirror image of the right side. This way, when it is rotated, the symmetry-related spots on either side would show up at exactly the same time. By measuring both spots in a pair from the same crystal at the same time, we would eliminate a lot of the errors that come from compensating for different crystal sizes and radiation damage. When you fish a crystal out with a loop, you are lucky if it sits in your loop at all. There is no way to control its direction or even position in the loop. On most instruments, you can center the crystal in the beam, but there is no way to line up the crystal so that the diffraction spots would be symmetric. However, if you have an X-ray instrument that can rotate the entire assembly containing the crystal in its loop and metal base about different axes, you can first take a few test shots from which you can calculate the precise orientation of the crystal relative to the apparatus, and then use the motors that control the various axes of the instrument to line up the crystal perfectly about the beam, regardless of how it originally sat in the loop. We had used this device, called a kappa goniometer, at Brookhaven to do exactly this. The problem was that although the ESRF beamline in Grenoble was steadily improving, it didn't have one. I thought the answer to our problems was the beamline at the Advanced Photon Source, APS, at the Argonne National Laboratory, just outside Chicago, which had both the high intensity of the Grenoble beamline and a kappa goniometer. It was meticulously designed by the same Gerd Rosenbaum who, working with Ken Holmes, had built the first X-ray diffraction beamline at the DESI synchrotron in Hamburg. In the middle of October 1999, as soon as I realized we needed it, I wrote to Andrei Rokimiak, who oversaw the beamline, to ask if we could get some time on his machine. It had just become open to the public, but even before that, in the testing phase, I knew Ada had collected lots of data there. I didn't get an answer, so I wrote again in early November. He wrote me a brief reply saying that he would get back to me over the weekend, and the earliest time I could get was in the beginning of the next calendar year. I didn't hear back from him, so I tried again in late November. November turned into December, and I kept getting reports that the Yale group was slowly pulling ahead, Finally, in mid-December, I heard they'd had a little celebration on reaching 3.1 angstrom resolution. This meant they had cracked the problem, and they would be able to build an atomic structure into the maps. Finally, I'd heard they got even better data at the APS. New Year's Day of 2000 was a big worldwide celebration of the millennium, but I was despondent about our lack of progress. I felt like someone who had run a few good initial laps in a race, but was now falling inexorably behind. On January 3rd, Peter wrote to say he was giving a talk in Manchester and asked if I would like him to visit us in Cambridge to talk about their structure. Much as it hurt, I could hardly say no. It would be of tremendous interest to everyone, not just my group. I used the opportunity to ask him about the APS, and he said the data they had collected there was much better than anything they had obtained elsewhere. Right away, I knew that I had been right to ask for time there. I told Peter that I was stuck, and we had asked for time on the APS instrument as far back as mid-October, but had still not obtained a response to our request. Paul Sigler, the man who was pushed off the stage prematurely at the Seattle crystallography meeting 4 years earlier, was Peter's colleague at Yale. I knew he was a member of the committee that oversaw the APS beamline, and also that Andre had once been his postdoc. So I asked Peter if he could put in a word for us with Paul. I also wrote directly to Andre again and left a couple of messages on his phone. The next day, January 5th, I got a reply from Peter saying he would talk to Paul, which, considering its effect on me, sounds as biblical as it should. The following day, January 6th, Peter wrote saying that Paul had contacted the APS and hopefully they would be in touch shortly. The very next day, there was an email from Andre apologizing for the delay in replying to me, saying he had been very busy, but they could give me time in late March. That was almost 3 months hence, and would be 6 months since I had originally contacted Andre. It meant we had lost 6 months at a time when our chief competitors were using his beamline to get ahead. Still, it was an offer I couldn't refuse. 4 days later, on January 11th, I received shocking news. Paul had died of a massive heart attack on his way to work. Paul's death was a tragedy in many ways. He was a great figure in structural biology who had trained many superb scientists, and at the age of 65 was still relatively young, with many years of science ahead of him. The whole episode saddened me, but it also made me realize yet again how science depends on weird quirks of fate. If I had not written to Peter just the previous week, and Paul had not immediately interceded on our behalf, I am not sure Andre would have responded in a timely manner, and we might well have been completely out of the running for the first atomic structures. This was brought home to me soon afterwards, when, a couple of weeks later, I had to give a talk at the ESRF synchrotron in Grenoble at a meeting for their users, and both Ada and I were invited to talk. I wouldn't have shown our latest research anyway, but it didn't matter, as I had nothing new to report. So I gave a talk based on what we had already published a few months earlier. After my first slide, I heard a click and turned around to see someone from the audience taking a photograph. I thought he was possibly reporting for the synchrotron newsletter, but then I heard a click after the next slide, and then after every single one. The guy turned out to be someone who had worked with some of Ada's group in Hamburg. When I wrote to him and said I'd be happy to send him a copy of my talk, he said he had been asked by former colleagues to give a small report about my talk.
We'll be just 2 more minutes and we'll be wrapping up after this chapter, at the end of chapter 12.
It is considered very bad form to take pictures of someone's talk without their permission. They must have felt the stakes were high enough to get someone to do this, but in this case, they didn't get a thing from me that wasn't published. In an amusing coda to this, a year later, when the structure was finished and published, I gave a talk at the same venue. As soon as I started, a young woman took a picture. Thoroughly irritated, I stopped and said there was no need to take any pictures and she could have a CD of my talk if she wanted. The ESRF director came up from the front row and apologized to me, saying she was just the photographer for their newsletter. In any case, right after my talk, Ada spoke, and it immediately became clear that I had badly underestimated her tenacity when I had ruled her out of the competition. Her maps had improved considerably from the previous summer in Denmark, and were now actually better than anything we had. Clearly, whatever problems she may have had earlier, she seemed to be making progress now. Her maps still weren't good enough to start building an atomic structure, but there was no telling how long it would be before she got to that stage. Much of her new data had been collected at the APS on the same instrument where we had finally obtained some time. I went back, realizing that our 2 days at the APS would be absolutely crucial. We could not afford to fail, and we could not leave anything to chance, since otherwise we might never be able to catch up. In a heroic effort, Bill, with help from Rob and Johnny Cash, froze hundreds of crystals and stored them away in dewars. We had created a spreadsheet so each crystal could be located precisely in its dewar. Every other one was screened at the Daresbury synchrotron for quality and cell dimensions. The ones that had matching cell dimensions and diffracted well were considered keepers and gave us an idea of how many usable crystals we had for each heavy atom soak. Not content with this, I persuaded Bill to go to the Brookhaven synchrotron by himself and collect actual data from representative crystals for each compound. After an exhausting 48 hours without sleep, he obtained data showing that all the compounds were bound as expected. With 3 dewars full of decent crystals, we were ready for our make-or-break trip.
All right, pretty cool. Lots of details. I was a little disappointed. I thought he was going to spend more time in Utah. I was a little bit of a surprise there. Again, I haven't previewed the book. I haven't read the book, and we have an agile approach here. You can hear the AC running over there. If it turns out to be not the right book, not the right approach, then we won't do a second reviewing of it. I'm really impressed so far. I mean, I haven't quite understood it all, but the value of the research of the laboratories from the research into, well, it started as atomic weapons, but became atomic energy overall, uranium enrichment, etc., how valuable all of that has been, just the use of heavy water molecules in particular, in getting images. And it makes you think, what does it mean to even see something? What does it mean to see something? It becomes a lot of philosophy to that, because you can't actually see these things. We're actually creating something that we can see at the scale that we usually see things at, when in reality it's interpretation of a variety of data that's collected. It's pretty phenomenal. I wonder. There's 3 hours left in the book. I wonder if this book will get into expanding on the variations of how ribosomes may work within cells, the variations about how ribosomes may work based upon epigenetic factors and so on. That will be interesting. Or is this? I seriously doubt that Venki ends this as one ribosome to rule them all. That said, so far, really valuable. It's a good thing to listen to while going about other work, even if it doesn't all sink in. And interesting to hear about just another scientist and their approach to the work. So with that said, not for everyone, but we have about 3 hours left. I'm going to shut this stream down here, and we don't know what the day may bring. But that said, thanks for joining. Copies of this are also on BitChute and Rumble for those who are interested. Again, Venki Ramakrishnan, Gene Machine. By the way, he has a sister who's also very senior in the Wellcome Trust, I suppose, and his trying to get information about his parents, who were also, I think, his father actually had a Rockefeller scholarship at one point, which is one of the reasons why the family relocated early on from India to Washington State, I believe, in California. But there's no doubt that Venki is the most accomplished person thus far in this family. So with that said, everyone, thank you very much. Have a good day. Might see you in a little bit. Might not. Either way, stay safe, stay happy, stay productive. Take the high road. You know what I mean. All right, guys. Love you.